Welcome back. This is video 7. This video is all of the course content on methane. To begin, we're going to repeat an earlier section that introduced us to methane. Methane, CH4, has an absorption band at 7.6 microns here, which is greenhouse warming, and close to the thermal peak around 10 microns here. Half of this band overlaps with 100% absorption by water vapor, which reduces methane's impact. The methane band is not 100% absorbing, whereas the carbon dioxide 15 micron band is 100% absorbing and wide. So the present concentration of carbon dioxide has more absorption and has produced higher greenhouse gas global warming than the present concentration of methane, but the incremental impact of methane is higher. Websites say that methane in the atmosphere is a much stronger absorber of Earth's thermal infrared radiation than carbon dioxide. They may not say so, but I believe this is for new emissions adding to the present concentrations of about 1.9 parts per million methane and 420 parts per million of carbon dioxide. 200 times more carbon dioxide. Section 34. Is methane absorption stronger than carbon dioxide? And if so, why? Carbon dioxide remains in the atmosphere much longer than methane. Hundreds of years to perhaps 1,000 years for carbon dioxide to get removed by plants, mainly trees, and cold regions of the ocean, though I cannot find a good number and source, versus 8 to 12 years or so for methane to get broken down, oxidized to carbon dioxide and water vapor in the atmosphere. If methane is a stronger absorber than carbon dioxide, and we emit a large one-time emission of methane, the absorption effect will be strongest immediately after the emission, and then fall over years and a couple decades, and finally it becomes carbon dioxide and water vapor, which are both also greenhouse gases. Sites typically give the relative absorption and radiative forcing impact, the global warming potential, of a new one-time pulse emission of methane versus the identical mass of carbon dioxide as 100 to 120 over the first year after emission, 80 times over the first 20 years, and 28 or 25 times over the first 100 years. These comparisons are per ton of emission, not per molecule, not per part per million, not per ton of carbon, and with the implied condition of the present concentrations in the atmosphere. Let's see if we can verify the 1-year number for ourselves. First, we change the numbers from per ton to per molecule, with carbon dioxide having 2.75 times the molecular weight of methane. We divide the first number, 100 to 120, by 2.75, and we get 36 to 44 times per molecule. So, is methane absorption 36 to 44 times higher per molecule, or per part per million, than carbon dioxide? One top university says Yes, and gives their reason that methane has more bonds than carbon dioxide and so more vibrational modes. I believe this is completely the wrong reason. I did calculations from high-tran spectral line intensities. If there were no greenhouse gases in the atmosphere, my calculations, which could be wrong, say that carbon dioxide would absorb about 5 times as much of Earth's thermal infrared radiation than methane on a per molecule basis near Earth's surface. So 1.7 times as much per ton. But the atmosphere is not devoid of water vapor, carbon dioxide, and methane. Carbon dioxide concentration reached 420 parts per million in 2022. The atmosphere is fully absorbing between 14 and 16 microns due to existing carbon dioxide, and fully absorbing between 5.3 and 7.5 microns due to existing water vapor. So it is the range 7.5 to 14 microns, the green box in the diagram, that matters most for new emissions of methane and carbon dioxide. This includes half of the methane band and one wing of the carbon dioxide 15 micron band. I used high-tran spectral line intensities and calculated that within this range, 7.5 to 14 microns, a molecule of methane near Earth's surface would absorb about 17 times more of Earth's thermal radiation than a molecule of carbon dioxide. A ton of methane would absorb about 46 times more thermal radiation than a ton of carbon dioxide, a little less than half the published numbers. There are some subtleties, and I may have some details wrong. My numbers would be higher if I changed 14 microns to, say, 13.8 microns, but I don't think my numbers would double. The figures reported in websites seem plausible within a factor of 2.6, but the reason is subtle. I believe the actual reason for carbon dioxide's relatively weak absorption is that carbon dioxide's absorption cross-section at 14 microns, the approximate edge of the 100% absorption band at present concentration, is much less than at 15 microns. 15 microns, 14 microns for carbon dioxide. But methane and carbon dioxide are only partially absorbing in this wavelength range, 7.5 microns to 14 microns. So absorption happens at all altitudes in the atmosphere, across which pressure, density, temperature, and methane concentration vary. So my simple analysis was too simplistic. I used a public modeling tool, ModTran, that calculates absorption and transmission using a realistic model of the atmosphere, but a single ground temperature. I found that adding another long-term 2 part per million of methane to the atmosphere caused 28 times the heating effect as adding another 2 part per million of carbon dioxide. So that's on a per molecule basis. This would be 80 times on a per ton basis. I got those numbers using the U.S. standard locality in ModTran, but this would vary with locality setting. No single locality in ModTran represents the entire world. And then there is the complication of clouds and precipitation and different surface temperatures at different locations. So the figures reported in websites seem plausible to me, but subtle and tricky. Now let's see if we can verify the 100-year number for ourselves. Let's assume an impulse emission of, say, 1 ton of methane, which decays exponentially to 0, creating water and carbon dioxide. Ultimately, 2.75 tons of carbon dioxide. We integrate the concentrations times their respective short-term global warming potentials over some time interval. Then we sum them and divide by the time interval. Then we fudge some numbers to get the numbers that climate scientists use. I was able to get global warming potential numbers of 120, 77, and 25 for 1 year, 20 years, and 100 years by making two assumptions. The first assumption is that the 1 year value is 120, not 100, not 80. The second assumption is that methane's decay time constant is 18.6 years, not 10 years, 12 years, or the range 8 to 12 years given by various sources. Though this agrees well enough with the IPCC's GWP numbers, it is complicated and confusing. Supposedly, methane's oxidation in the atmosphere is a complicated multi-step process. It gets oxidized first by a hydroxyl radical in the atmosphere, not by an oxygen, ozone, or water molecule. The hydroxyl radical is not a stable species in the atmosphere. I assume hydroxyl is formed by ultraviolet light dissociating water, but I don't know. What about lightning? Then there are other steps before the final state of carbon dioxide and water molecules. The intermediate products have their own absorption spectra. Supposedly, there is some feedback process whereby the higher the methane concentration, the longer it takes to oxidize the methane. It's complicated, and I didn't try to learn about it yet. Climate scientists refer to methane's perturbation lifetime in the atmosphere. The orange curve in this graph. It's around 12 years at present time and concentration, but increasing with higher concentrations in future. And concentrations have increased with time. I definitely don't understand this, and it's not worth my time and interest at this time, and it would not give a time of 18.6 years now or in this century. So I don't understand methane's perturbation lifetime and therefore the GWP numbers. However, regardless of my difficulties, at present concentrations, the emission of methane in a year has more impact short-term and long-term than emitting the same amount of carbon dioxide, whether same in mass or same in part per million, according to mainstream climate scientists. Now, this does not mean that a given atmospheric concentration of only methane would give more warming than the same concentration of only carbon dioxide. It would give less warming, about half as much for 400 parts per million, according to one source and the ModTran tool. So it's tricky and confusing. How would doubling the current concentration of methane compare to doubling the current concentration of carbon dioxide? Doubling carbon dioxide would have the stronger effect, but of course its concentration is already 200 times that of methane. So, methane is both stronger and weaker than carbon dioxide, depending on exact wording and on implicit conditions. Regardless, methane does add to heating, and it is a significant component of global warming. Here is a tool, Slugulator, that you can use to see the effect of emitting a one-time slug of methane. If you want to read more about methane's global warming potential, here are some articles from MIT and Stanford, and also a contrarian or skeptical position. Section 35. Methane concentration, emissions, and goals. Methane is emitted to the atmosphere from natural and human-caused sources. Bacteria in landfills and wetlands, which have increased their emissions as Earth's surface temperature has increased while they remain wet. Emissions from agriculture and burping by cows and other ruminants. Oil wells venting natural gas. Coal mines leaking natural gas. Leaks from gas wells and gas pipelines. And thawing of permafrost in future. Methane gets broken down, oxidized, to carbon dioxide and water vapor in the atmosphere. Methane concentration was about 0.7 parts per million, or 700 parts per billion, before the Industrial Revolution, and was about 1.9 part per million, 1900 parts per billion, in 2022. Almost triple the pre-industrial concentration. Here is the concentration since 1850. Increase in concentration accelerated up to about 1984, then slowed. The increase was slow from between 1991 and 2014, but seems to have picked up since then. Methane emission numbers and graphs are trickier than concentration numbers and graphs. They might include all emission sources, natural and human-caused, or only some, and there are different reporting units. Beware, 1 gigaton of carbon, GTC, of methane, is 1.33 gigatons of methane, GTCH4. And 1 gigaton of methane, GTCH4, is about 25-ish GTCO2 equivalent. Methane emission numbers seem often to be given in megatons or gigatons of carbon dioxide equivalent, which is the mass of the methane emission times methane's global warming potential for some length of time. The IPCC requires countries to use the value 25 as the 100-year global warming potential, but you may see 28 or higher values, such as 40 and shorter timescales. Very confusing for us laymen. This graph of methane emissions through 2023 is given in megatons of carbon dioxide equivalent, presumably using 25 as the conversion. I believe this graph only shows the 60% of emissions coming from human sources, not the 40% coming from natural sources, but I did not verify that. This chart shows 2020 methane emissions as 9,500 megatons of carbon dioxide equivalent, so about 380 megatons of methane. But I believe the emission, including natural sources, was about 580 megatons of methane. Methane data is confusing for us laymen. The Global Methane Pledge, GMP, aims to cut global methane emissions by at least 30% from 2020 levels by 2030. So here's 2020, and they want to cut it by a third, so they want to end up with a level around here. That would be a huge cut and seems to me unlikely to be met. I don't know if there is a numerical target. I don't know if the goal includes natural emissions or only human-caused. Section 36, Methane Emission Sources. This 2023 chart shows the estimated contribution to methane emissions from different sources. I don't know how accurate this data is. The two blue bars here and there are methane emission contributions from natural sources. The other bars are human-caused, anthropogenic. The largest source is emissions from wetlands, swamp gas emitted by bacteria, and these emissions increase with rising temperature and rising wetness. I assume we will not reduce this component, which means reducing the other components even more. The second largest source and the largest anthropogenic source is emissions from agriculture. Here. This includes decay of biomass, burps from cows and other ruminants, and decay of farm animal wastes, I assume. There are some efforts to reduce these emissions, but I assume the impact will be minor. The next component is the energy sector, with 22% of the methane emissions. These are uncontrolled natural gas venting and leaks from oil wells, natural gas escaping from coal mining, and leaks from natural gas wells, pipelines, and valves. These leaks are not necessary or useful, except that fixing them adds costs. Though not the largest component of methane emissions, the energy sector gets attention for future reduction of emissions. More on this in the next section. Electric power plants that burn natural gas emit less carbon dioxide per unit of electric power generation than plants that use coal. But natural gas leaks in the supply system complicate the assessment of whether natural gas power plants are actually better than coal for global warming. This also impacts the assessment of how green electric vehicles should be considered when they charge from the grid. The fourth bar is labeled waste. I believe this is primarily bacterial emissions from garbage landfills. Some landfills are covered with plastic sheeting and capture their methane rather than emitting it. If thawing permafrost in Russia and Canada releases a lot of methane over a vast area in future, that would add to global warming. One article I read said that this would be smaller than present methane emissions because emissions are likely to be slow, but continue over a long period. Methane emitted by bacteria, archaea, has a different carbon isotopic signature than natural gas from fossil fuels. Recently, this has allowed scientists to estimate the fraction of emissions from the energy sector versus the other sources. Section 37, Reducing Methane. The global emission rates are about 580 million metric tons per year of methane, human-caused and natural sources, and 41 billion metric tons per year of carbon dioxide. So 70 times higher carbon dioxide emission tonnage, but the 100-year radiative forcing impact of methane is 25 to 28 times higher per ton. And the 20-year global warming potential is about 80. Both emissions are important, but we can't assign each a fraction of impact without other assumptions. Methane gets broken down, oxidized to carbon dioxide and water vapor in the atmosphere with an 8 to 12 year or so time constant, not half-life. So we would think that about 10% of atmospheric methane breaks down each year. Present emissions, natural and human-caused, exceed the amount that gets broken down, but not by very much. Methane concentration rises more slowly than a naive calculation from emissions due to its removal rate. If we could reduce total methane emission by 10 to 20%, I calculate that methane concentration should stabilize or decline, but it's not that simple. Let's estimate that 70% of emissions are not amenable to reductions. Then we would need a 33% reduction in the amenable 30% to reduce by 10% total. But if only 10% of emissions seems feasible for reductions, we would need to reduce that component to zero. But reducing any component to zero will be economically infeasible. We should prioritize the greatest reductions from all sources at the least cost. And if we would need a 20% reduction in total methane emissions, including from wetlands, that might be infeasible. If human-caused climate change and global warming is true, is important, and if it can be significantly ameliorated, we should presumably reduce what emissions we practically can of each greenhouse gas, informed by good data and scientific consensus on how to get the most benefit for the cost, and on the impact of the reductions. A few scientists think the impact of reductions would be too small for the immense costs. The denialist position, it is difficult for us laymen to assess. The energy sector is not the largest source of methane emissions, but their venting and leaks are unnecessary for the service they provide and seem technically amenable to great reductions, though at some costs. First, the venting and leaks must be identified, quantified, costs determined, and prioritized. There are now satellites to map methane emissions throughout the world, including MethaneSat, which launched in March 2024 and will provide data in 2025. And there are drones for local pinpointing. Since late 2023, satellites detected about 20,000 sites worldwide that qualify as super emitters, sites hemorrhaging at 100 kilograms, 220 pounds or more of methane per hour. Together, these emit over 18 megatons per year to no purpose. Stopping emissions for these 20,000 sites would reduce global emissions by at least 3%. It is easy to say, yes, go fix these, but costs would be in the billions of dollars. Hopefully, countries and companies will plug their largest leaks, but this requires acceptance, will, and policy direction on a global basis. A corporation makes more profit by ignoring leaks when they don't pose a risk of explosion than fixing them unless governments impose a cost on those emissions. Venting and leaks can occur at oil or gas wells, on land or sea, at coal mines, at pipelines above ground or underground, valves, or other infrastructure. The U.S. has something like 250,000 old wells. It can cost over $1 million to properly seal an old well. I don't know if the U.S. generally forces companies to properly seal their old wells. The federal government has budgeted $1 billion for sealing old wells' natural gas leaks or venting, which will seal up to 900 wells out of 250,000. I don't know how many super emitter sites are in the United States. Repairing a leaking underground pipeline can cost $1 to $10 million per mile. As a safety issue, a utility has incentives to fix leaks that become dangerous to the public. Section 38. Methane uncertainty, skepticism, and denial. Methane's perturbation lifetime and global warming potential are complicated and very difficult for us laymen to understand and believe. Since I don't understand them, I assume there may be significant uncertainty as well, but actually, I just can't follow it. I cannot tell how much certainty or uncertainty there is in the emission amounts from different sources. Perhaps isotopic analysis will reduce uncertainty in the amounts of emissions attributable to fossil fuel sources. A few climate change skeptic scientists think the benefit of methane reductions would be too small for the immense costs. This is difficult for us laymen to assess. And here are two skeptical articles. Beware that a published paper that looks authoritative may not be correct per mainstream climate scientists. However, neither is it easy to find published rebuttals of articles that climate scientists deem denialist. This is difficult for us laymen as we are trying to learn and make sense of this subject. I am not a climate scientist or a scientist at all, and I could have made foolish mistakes or failed to understand subtle but critical issues. I hope this course has given you useful information. My other videos are various physics courses.